Yeah, welcome back. We are now wrapping up this section of momentum and impulse, which is normally question number 4 in a normal question paper. Let's look at what we did so far before we can answer exam type questions. We talked about momentum, that the momentum by definition is come from the formula of P equals to mv, which means that is the product of mass of an object and its velocity. And again, about momentum, we know that the unit is kilogram meters per second. That's what we know again. And then the third one is that momentum is a vector. So what gives it the vector property is the velocity in this one. So that's what we know about momentum first. The second one was that momentum can change. We can have change in momentum. Which is our delta P. Now change in momentum, we say momentum can change. And how do you calculate the change in momentum? We are using this expression of saying delta P will be the final momentum minus the initial momentum. Remember, momentum can change when there is an increase in velocity, also when there is a decrease in velocity, and then also when the velocity changes direction. So velocity changes direction. Now there is another part also in this case where now we're talking about graphical representation. So graphical representation of momentum, remember the golden rule we say, make sure that when you draw the initial and final, they are all starting at the same point. If the initial is going this way to the right or east, also the final, if there's an increase in momentum, will go to the east again or to the right. And then when you find the delta P, you always start from the head of the initial to the head of the final. That our final delta P will be this. That is my delta P. In all cases, this will be the case. Start from the same point in this case, and then draw initial according to the direction and final according to the direction, and then now join the head of initial to the head of the final. You will never go wrong if you go that route. Again, we know we also learned that a change in momentum here can be the same as impulse. That's where now we came up with the formula of saying impulse will be F delta T, F net delta T. Now if impulse goes to F net delta T, therefore it means that now the F net delta T will be the same as delta P. Very important relationship. Yes, the impulse equals to change in momentum, and by definition from the formula of impulse we can know that the impulse will be now the product of the net force acting on an object and the time it takes while in contact with the object, or the time interval while the force acts. So that is the question of impulse and change in momentum. Very important relationship there. You can even define Newton's second law using this. Again, this is the case when you define that Newton's second law to say, oh, F net equals to delta P over this one. So net force acting on an object equals to the rate of change in momentum, and the change is in the direction of the net force. Now from this one we also came to collisions. We said we have got two types of collisions. The collision can be elastic, or the collision can be inelastic. If you still remember, we said elastic, it means that now both the kinetic energy, the total kinetic energy initially equals to the total kinetic energy final. Fine. And also the second one is that momentum is conserved. Momentum is conserved. Conservation, remember, conserved, we said sigma pi will be the same as sigma pf. These are the two expressions in the elastic collision. Whereas in the inelastic collision, we know that also momentum is conserved. Yes, in both collision, momentum is conserved. That's what you should know. Momentum is conserved. But in the case of inelastic, we say the total kinetic energy is not conserved. Therefore, Ek phi initial is not the same as sigma Ek final. That's the case. That's what you should know when you're dealing with the two. They mean that if they can ask you to prove whether collision is elastic or inelastic, you are not going to use momentum. No, because in both cases, momentum is conserved. So what it will make the difference between the two collisions will be the kinetic energy. You have to find the kinetic energy initially. Just calculate. You find if the two objects are separate, delta Ek. I will be the Ek of the first object plus the Ek of the second object. In this case, Eki of the first object, Eki of this one, second object. Then you find the value there in joules. What you need to do, you continue again, find the total kinetic energy after collision. Then you find that Ek of A final plus the Ek of B final. So you get the joules here. You compare the two. Obviously, the two are not going to be the same. Then you will tell the examiner that, oh, fine, because the kinetic energy initial and this one others, and then you say, therefore, collision is inelastic, since in this case, then the sigma Ek I is not the same as the sigma EKF. Sorry for that one. Yeah, that is how you do the collisions here. You want to prove that collision is elastic or inelastic, you are using kinetic energy. You will have to determine whether is it conserved or not conserved. So now the last part in momentum was the conservation. The conservation of momentum. Well, that's where many questions will be coming from. Conservation of momentum. We said yes, momentum can be conserved. There are only 3 scenarios that you should know. We said, but in all the 3 scenarios, please start with the principle sigma pi equals to sigma pf. That's the case. Therefore, otherwise, then you can start with your, now the first is a scenario of your mv plus mv equals to mv plus mv. And the second scenario will be your mv plus mv equals to m plus m all multiplied by v. The last one will be m plus m multiplied by v equals to mv plus mv. Because they are all mv's, then you have to now differentiate which one are you talking about. You can have m1 v1i and m2 v2i, m1 v1f and m2 v2f, m1 v1i, m2 v2i, m1 m2 vf, m1 m2 vi, m1 v1f, m2 v2f. That's how you differentiate which velocity are you talking about. That is the conservation of momentum. Remember, there's this one they can ask you to define it. Very important will be the keywords in this definition, where now you say in an isolated system. The isolated system should be there. Whether it comes from the first of the definition or at the end, no problem. In an isolated system, total, the word total should be there. Total linear is optional. Momentum is conserved. So very important words there will be isolated system, the total, and momentum is conserved. So the 3 keywords are very important. So once you define this one, now we can just start to say total linear momentum is conserved in an isolated system. So that's why I say you can start with isolated system or finish with it, no problem. That's how we define. And then from here, once you have dealt with this one, now it will be the question of now dealing with the question from the exams. So to deal with those questions, let's just pause and then we'll now deal with the real questions when we come back.